All right, page 8, at the top of the page. Okay, remember, we just finished up figuring out what static pressure is, right? So let's do a quick review. Quick review. Okay, density equals mass over volume. Pressure equals force over area. The pressure in a static fluid is equal to the pressure that's on top of that fluid plus rho GH, which is the gravitational effect that causes more pressure, right? The extra weight on top, extra pressure because of the fluid that's you're holding up. Okay, now remember, that's got a name and that's got a name. Absolute. And what's that one? Okay, absolute and gauge pressure. The gauge pressure, remember, does not include, usually that's atmosphere on top. The P naught on top is usually the atmospheric pressure, okay? Like for our everyday occurrences that we're going to be measuring pressure, that pressure on top is usually atmospheric, okay?
But it could also be, I guess, somebody just like pressing or something.
Well, like for instance, if you have some sort of closed container, this pressure up here might not be atmospheric pressure. It might be something else. So if you were down here, then this will be rho GH, just like before. And this is whatever that pressure is inside this closed container for the air or whatever it is on top. Right? And it could be atmospheric, it might not, but in most cases that will be atmospheric. And another example, what if you had something like this? What if you were right down here, okay? And let's say this is water, and this is oil, and then you got air up here. You really got three pressures, right? So how would you do that? Yeah, you'd have a rho GH for the water, you'd have a rho GH for the oil, and then because the air, we'd assume it would be atmospheric, you'd add one atmosphere to the top, right? That's your P naught, okay? That's how you would do that if you had multiples. All right? Now, there is a possibility, occasionally you'll run into a problem that'll look like this, okay? Where you'll have a tube, all right? And you'll have a liquid over here and a liquid over here, and they may not be the same height.
That means there has to be more pressure on that.
Yeah, so like there's a couple of ways that this could happen, okay? A couple of ways that this could happen. Way number one. Well, you explain it to me. How is this possible for it to be static like this?
More pressure on the right side.
Yeah, there has to be more pressure here. This pressure on the right would have to be greater than the pressure on the left, right? Yeah. Correct, I mean? Okay. That's one possibility. So pressure on the right would have to be greater than the pressure on the left. There's another possibility, and that possibility would be that if you have a fluid here and a fluid here, and they're two different fluids, okay? Say one might be mercury and one might be water, okay? In that case, you would have a different height because they have a different density. Now, right here where the two meet, if it's static, what has to be true about the pressure in the mercury and the pressure in the water? Has to be equal, right? So we know that the pressure all the way straight across here is all going to be the same, right? So we could figure out rho GH for the mercury here, correct? Yeah. And then over here, all the way across here, from here to here, we would figure out the rho GH for the water. Okay? And those two would have to be the same for it to be static. Okay, so that's a possibility where, because the mercury weighs more, it has more density, it will sink farther down, and it'll have a smaller height here because it has a much greater density. So it'll have to have a smaller height. And then the water levels won't necessarily be water levels, they'll be fluid levels, won't be the same on either side. Okay, does that make sense? So you have those two possibilities, either the same fluid all the way throughout, more pressure here, or you have to have a greater density fluid on this side. All right, so in case you run across one of them. Now, here's my next question. We've already actually done this. I want to make sure you understand it. Okay, something like this shows up. All right. If this is a mass M and this is an area A, and this is a gas inside here, gas, okay, and this is a height H. You remember how to find the pressure inside that gas?
Well, force over area plus 1 ATM.
We have 12.
Okay, everybody do that. Find the pressure inside that gas. How would you find the pressure inside that gas?
It's just not. I know we.
What did you get again?
mg over a.
mg
Over
M.
over a.
M.
Oh, why didn't I write rho?
Subconscious.
mg over a,
plus 100,000.
Yeah.
Plus 100,000.
Pascal.
which is 1 atmosphere.
Yeah.
All right? Okay, because you have, if you draw the piston, you have the pressure from the air, you have the pressure due to the mass, and that has to be balanced by the pressure in the gas, right? Okay, piece of cake. All right, don't forget that, because that, we studied that in,
Gas laws.
yeah, we studied that in gas laws, but since gas is a fluid, I mean, the same thing would be true if we contained this thing with liquid instead, right? Still be the same thing, right? All right. Now, this is important because we need to talk about what's called Pascal's principle.
Oh, I hate Pascal. High school, not high school. Wonderful.
Principle. Principal. All right, Pascal's principle. All right, Pascal's principle simply states this. If you apply this extra pressure to a fluid, whether it be a gas or a liquid, then this extra pressure will be distributed throughout the entire gas. So if this was a liquid in here, okay, then down here at the bottom, what would be the pressure at the bottom?
Same as the top.
Would it be exactly the same as the top?
Because I mean, there's a.
It would be, this is the pressure right here, right?
Yes.
No, because one's holding up the other.
Yeah, but the pressure at the bottom has to hold up all that plus the liquid.
That's
or
what I'm
our
saying.
fluid.
That's
Yeah,
what I'm
yeah,
saying.
yeah. So the pressure at the bottom would equal, would equal the pressure at the top plus rho GH, right? And the pressure at the top is this business, right? Does that make sense? Okay, so remember, I erased it, but right here. This is not necessarily just atmospheric pressure, 100,000 pascals, right? Because if we put something else on top to add more pressure, that gets distributed throughout the entire fluid, right?
What's the actual one? How big is that?
It's 101,325. I think I wrote it down.
Yeah.
Colin was mad at me because I wrote it down different in different places. It's 101,325. I think one time I wrote it down 101,352. So it's 101,325. Okay, for e-homework. All right, now this is really important because what this does is pressure at one location gets distributed throughout. Okay? The pressure added at one area will equal the pressure added at the other area. Now this is really cool because that allows us to do something like this. If you have a cylinder here and you apply a force over an area, Force 1 over area 1. Okay? That pressure gets distributed throughout. So if I connect it through a tube to another cylinder,
Well,
okay? Then this pressure gets distributed through here, and then out through here, right? So if I have another piston over here, this has area 2, and I'm going to get force 2 out over here. Now, by the way, this is one important thing on how this works. This, your blood circulatory system works this way. Your heart beats. Your heart applies pressure at one spot. That gets distributed throughout your system, right? To move the blood everywhere, right? So if you push down here, that's going to distribute out over here. So the pressure here must equal the pressure here. Now, I'm having these at the exact same height, so that I don't have to worry about this rho GH business, right? Okay? Because actually the pressure down here will be greater than the pressure up here, right?
so if you connect the tube higher, it's going to go less.
Yeah, so like if this piston starts off down here, then the pressure here won't be the same as the pressure here because there'll be a rho GH difference, right? So these have the same height, so I just pressure here equals pressure here, okay? Now look, but pressure here is F1 over A1, and the pressure here is F2 over A2, correct? Let's rewrite that. That's force 1 over A1, but A2 is really big.
So F1 has to be even bigger.
So F2 must be proportionally bigger. So that this F over this A equals this F over this A. Does that make
So
sense?
Pascal's principle is P1 equals P2 at the same height.
Yeah, as long as you're at the same height. That's correct. As long as you're at the same height.
And then now we have to do it at rho GH.
Yeah, maybe. Usually if they give you a Pascal's principle problem, they'll have it at the same height, so you don't have to really have to worry about it. And in most cases, the pressure that is applied here will be so great in comparison to the height difference that we generally neglect it. Okay, unless there's a sizable height difference. Okay? Because what you'll end up with usually is a really huge pressure added here. And so the change in height will be so small in comparison. We just generally, in most like equipment, we can neglect this. Now this business right here, in industrial purposes, is called either hydraulics or pneumatics. This is how your brakes work in your car. You step on the brake. What you're doing is pushing fluid through a tube, and then your brake pad's over here, and the brake pad pushes against the disc or the drum inside the tire to slow your car down. Now, it's safe to say that if you had to put your foot against the disc brake or the drum inside the tire, actually most cars now have disc brakes all around. If you had to take your foot and push it against the disc brake, like you might have seen in one of the Indiana Jones movies, I think the second one, where he sticks his foot on the brake pad to slow the runaway mine car down. You've got to push really hard. You are incapable of pushing hard enough to slow your car down. So what we do is we magnify your force.
Wait, to slow it down?
Well, you can slow it down some.
You wouldn't slow it down, but it wouldn't slow it down fast enough to avoid crash. Wow. So this device, hydraulics, we have brake fluid. You push the pedal down, and this pushes the brake pad against the brake disc, and it's high enough force so that, you know what a brake disc looks like, right?
Yeah.
Okay, you've got your tire, and inside your tire, you'll have a little metal disc. You can see it through the spokes of your rims sometimes. And then you got this little device that sits around here. And if you look at it from the end, this is the rotating disc right here. And it's got this horseshoe-shaped thing around it. And when you push on the brake pedal, a little tube comes in here. And a little tube pushes fluid in here and pushes these little pads right here against that rotating disc. And that friction causes your tire to stop spinning, right? And slows you down. Now, that's a lot of force. A whole lot of force. Okay? Now that seems like magic, by the way. We'll talk about that in just a second. it seems like it violates some sort of physics because we get magical big force from a little force. So let's say that you push with 1,000 newtons of force, and the area through which you push is like 0.0001 meters squared. What if the brake pad had a 0.01 meters squared area here? Then what would your force come out of the brakes? Yeah, it would be 100 times greater, right?
100,000.
So you'd end up with 100,000 newtons pushing the brake pads. Magic. Okay? The magic of hydraulics and pneumatics. It's pneumatics if it's air in the tubes or in the cylinders instead of liquid. In big trucks like semis, sometimes you'll hear them and you'll hear their brakes bleeding out air when they come to a stop. Okay, yeah, they use pneumatics. And the reason why they use pneumatics is because it takes a whole lot of fluid to fill up all those lines to go all the way from where the driver is all the way to the brakes. And so they use pneumatics. And air is it's cheaper. You can just pump it right out of the air, right? Right out of the air. All right? So it's free. Okay. Now, somebody tell me, this appears that I have broken physics. Remember, we have this thing called conservation of energy that always tells us that you don't get anything for free, right? That the energy you start with is the energy you end with. The only way you get more energy at the end is if you do work, right? So here I am, I've pushed this piston down from here to here, and I get this magical, magnificent, huge force out on the other end. What do I give up?
It's less distance.
Why less distance?
Because you're only pushing a little bit of air, and that air spreads out.
See, I'm only pushing this volume here, right? And since this cylinder is so much bigger, that means this volume here will be the same, but that means the distance it moves will be smaller. Now, force times distance here. Force 1 is small, the distance here is great. Over here, the force 2 is great, but the distance you get out is small. Force times distance, that's our work, right? So the work that goes in, at best, will equal the work that comes out of our brake system. Okay? You don't get anything for free. So what happens is how far do you push your brake pedal down?
Barely.
About that far, right? Goes about that far. How far do the brake pads move? Itty, itty bitty. They're like right up against the spinning disc. All right? They don't move very far at all. Okay? They don't move very far at all.
I thought you were
Okay.
supposed to push up.
All right. By the way, you all know Pascal's principle already, because you all know how to get toothpaste out of a toothpaste tube, right? Yeah. Where do you squeeze it?
The bottom.
Wherever you want to.
Yeah. The answer is wherever you want, because pressure applied anywhere to that fluid gets distributed everywhere, right?
No,
Evenly
eventually
throughout.
when you're trying to save money, you roll it up, and then you press it.
You just take a comb and you.
That's exactly what I do.
Straight up. I roll it up.
I bought that thing.
Mr.
I get.
We started last time, or we ended last time with this. An object submerged in a fluid. And we decided that the pressure on the bottom
Those legs. Oh, pressure.
the pressure on the bottom was greater than the pressure on the top. Okay?
Because of the height difference.
Because of the height difference. Because this pressure is P naught plus rho GH. And the pressure here is P naught plus rho GH. So the pressure is bigger. This marker's about heavy. So the pressure here is larger because the height is bigger. Now on the sides, it's going to balance out because they're pushing against each other and they have the identical heights, right? Now this is going to be true not just of a rectanguloid like I've drawn, but any shaped object. Okay, if you do the calculus to figure it out, there will always be a net pressure up that's greater than the net pressure down. The side pressures will always cancel. All right?
Well, what if you got it deeper than what it?
Okay, what happens is if you get it deeper and deeper and deeper, assuming that the density stays the same, then this delta height also stays the same. So the delta pressure also stays the same. So you get the exact same effect no matter how deep in, as long as it's completely submerged.
Oh, the change in the height you're talking about is the height of the object.
Yes, this delta height, this height difference is the height of the object, right? And this, because this height is the height to the top and this height is the height to the bottom. Does that make sense?
Yes.
We got it?
So it's always
All right.
going to have that constant height difference. So it's always going to have that constant difference.
Yeah, so once the object is submerged, this pressure difference never changes anymore as long as the density of the fluid stays the same. Now we're making an assumption that as you move deeper into the fluid, that the density of the fluid is going to remain relatively unchanged. Now that is not exactly true. Like if you start off, a meter deep in the ocean and go like, 1,000 meters deep, there will be a density change. Okay? So you technically will get more buoyancy force
Down.
push up as the deeper you go down. And this is why fish and subs are able to maintain an exact location. Fish have a bladder inside themselves that they can expand and contract, which changes their volume, which changes their buoyancy force, so they can float here, or they can float down here. And a sub does the same thing, because it has chambers inside the sub that it can fill with water, or expel the water out with compressed gas, and it can change its buoyancy force. And it can float at a certain level. Okay?
Smart fish.
Because there's a slight difference in density. Now, unless otherwise stated on the exams, we will assume that the density as we go deeper will remain the same. If they don't give you a new density, you'll have to assume it stays the same. All right?
Okay, so what does H represent?
This is the height of water above. This is the height of the water above. And the delta height is essentially the height of the object then. Does that make sense? All right, excellent. Now, let's just derive this quick. In fact, let me just, I think I can do it from memory. Okay, the delta pressure, delta pressure, then is going to be the pressure on the bottom minus the pressure on the top. Okay, the pressure on the bottom is P naught plus rho g height to the bottom minus P naught plus rho g h to the top. Everybody okay with that? There's the pressure at the top and the bottom. Does everybody see that the pressure at the above, P naught, the air pressure on top, is going to be the same in both cases? Right?
So now it's PGH rho GH minus rho GH.
So it's just going to be rho gh minus rho gh, right? So I'm going to get rho g, that's delta h then, right? The difference between those two, assuming the density stays the same. Okay, so the change in pressure between the two is just going to be rho g delta h. Now,
Now we get
Wait, well, wouldn't delta H be negative?
I did bottom minus top.
wait.
The bigger one
H
minus
bottom is the height, the deepness of the water below.
Yes. Okay. Now that's a good point. I should bring this up. A lot of students get confused by the letter H. H is height, but when we're talking about this, we're really talking about D, depth, right? H is the height of water above, so it's like how deep you are in the water. That's what it really is. So it's the height of water above.
And in this case, it's the height of the water below. For P bottom,
So
H bottom.
this H is the height of water, or the depth of water, from the surface to the bottom of the object. This H is from the top of the water to the top of the object.
Oh, I'm way off.
Got it?
So then the deeper, the bigger
Delta H is just the height.
So delta H is just the height of the object.
But
Okay, got it?
Isn't it objects with lower density in the water always float no matter what?
Objects with lower density always float. Yeah, we're going to talk about that in just a minute. Lower density than water will always float. That's true. All right. You ready?
Yes.
Gonna do a little fancy thing here. Gonna multiply by area.
Get a pose.
Okay? The area is the area of the top of the object. Okay? Okay, what's a pressure times an area? That's a force. What is a rho G delta H times A?
Volume.
A, because this is delta H, right? And A is the area of the top, so that's the volume of the object. Rho GV. Now the way they usually write it is this way. They call this buoyancy force, and it's rho VG is the way they normally write it. Okay, rho VG. Now everybody, let's make sure we understand this because this is where you'll get confused sometimes. This is the force that pushes an object up if it's in a fluid. Any fluid. Are you in a fluid?
Yes.
I'm in gas.
So you're in gas. That's correct. So do you receive a buoyancy force?
Yes.
Which way is that buoyancy force?
Everywhere.
Up. Why don't you float?
Because
you're
it's not
Fat.
enough.
We're fat.
Yeah, because you're more dense. That's right, you're fat. You're more dense than the air that you're in, right?
So actually, you're pretty skinny.
lose weight right now.
All right, now, if you had a large enough volume,
If you were fat enough, you would float.
no, if you had a large enough volume, could you float in air?
Your density?
If your
Yes.
density main peak, basically.
We're talking about that density thing in just a
Be
minute.
fat with a very high.
Does a blimp weigh anything?
No.
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 Yes, a blimp does weigh something.
Completely mad.
Even the air in the blimp weighs something.
That's correct. And the helium in the blimp weighs something. In fact, it's thousands of pounds of helium. But the deal is that it has such a large volume, it's a large enough buoyancy force that it floats. Actually, you can figure out your buoyancy force if you want. You can figure out your volume, okay? And you can figure out, this is your volume. This is the density of what?
Water and blood.
The whatever fluid you're in, right?
Gas, okay, now.
So this is the fluid you're in, which would be air. And this is 9.8. So you can figure out your buoyancy force. It turns out to be about a half a pound.
Fail.
So if you weigh yourself in a vacuum, you'll weigh a half a pound more than if you weigh yourself in air.
That's because you also have air in you, which is less.
That's what we tell girls about the weight.
Yeah.
If you grab a grocery bag, and you see your stove
Lying
on,
about your
and
mass.
then you grab the grocery bag and put it like that, it floats.
Yes, it does.
I did that. And then they fell, and then I got the fire. I was like,
All right, now listen. Okay, so we don't float in air. We do float in water. What's the difference?
Water.
Yeah,
more
we're
gas.
Okay, this is the density of the fluid, so please write this down. Fluid. It has nothing to do with you. It has everything to do with the fluid you're in.
It's not about you, it's about me.
I really hope I'm not in you.
Now.
That would be very weird.
This volume
Is the volume of
is this the volume of you?
Yeah.
Yes.
It has to be.
No, it's the volume of the fluid you're displacing.
It's the volume of the fluid that you're moving out of the way. Now, please be careful. We have a tendency to always say it's the volume of the object. It is not. Like, for instance, what's the buoyancy force of the swimming pool on me right now?
None.
None.
None. Why not?
Because you displace no.
Because I'm not in that fluid, right? Does that make sense?
yeah.
When will you get more buoyancy force from in being in a swimming pool? When you go down the steps and you're halfway covered up with water, or when you're all the way in the swimming pool?
All the
All the
way.
way in.
All the way in the swimming pool. It's because the volume displaced is
When you're
different.
drowning at the bottom
Yeah,
of the
wait.
pool. That's when
Yeah.
I just like water, like to keep water.
If you kick fast.
Okay, this is a classic trick question, everybody. Classic, classic. The volume is the displaced fluid. The volume of fluid that is displaced. So like for instance, if here's your body of water, and you have an object sitting there floating, or an object submerged, if the objects are the same size, which one gets the bigger buoyancy force?
That one I read in the red packet.
This one gets a bigger buoyancy force, so why doesn't it float?
Because it's not,
Rho GA.
its density is greater than its.
It just must be too heavy, right? Right. So here's the deal. This one, that's all the volume you're talking about. It's just the part that's submerged. Does that make sense? And you've noticed this, because you've noticed that when you're in a swimming pool, you have superhuman strength. You can pick people up, right?
Yeah.
No, I can't.
Yeah. Piece of cake. I can carry people around. But then as you lift them out of the water, what happens? Oh, kryptonite, right? You start to lose your superpowers. And when they're out of the water, you're just a normal human again, right? Okay, so when they're submerged, they get the buoyancy force. When they're only partially submerged, they only get part of the buoyancy force because they're only displacing part of their volume, right?
Okay,
Okay.
one thing. So that
Yes.
bottom one, it's not floating because it's heavier, so that means it has more mass, so it's more dense.
Yes. So if these two have the same volume of
But they're
object,
different mass, so its densities are different.
and let's make sure we get this correct. If something floats, what are the forces on the object? M, G, and buoyancy. What must be true of these two?
Equal.
They must be equal. Okay, now, if an object sinks, you've got buoyancy force. And you've got mg. But mg must be greater for it to sink, right? It's just forces all over again, right?
In a very mean way.
Wait, this answer.
And remember, once the object is fully submerged, then the buoyancy force has reached its maximum. And the force on the object, the buoyancy force, will remain constant throughout the fluid, assuming the density stays the same. All right? So, all right, so here's my question for you. Okay, I've got an object. The object here, we'll do this. Here's the object. Okay? The object is 0.1 meter this way and this way. And it's weighted at the bottom. Okay, so it has a low center of gravity. All right? And its height is
15.
15?
Mita?
All right, 15 meters. All right? It has a mass of
130.
130?
Kilo or gram?
Wow. Okay, 130 kilograms.
Very dense.
All right, now, tell me, if I put this in water,
I'm not talking about it's ugly.
okay, if I put this in water, will it float? Yes or no? And if it will float, how deep in the water will it sink? All right?
Well,
Okay, how do we do this?
That's the density.
Well, first you find the density.
yeah.
They have
Wait.
chips.
No. Put density of what?
It will float. No, is it in water?
Okay,
It will.
okay, just relax. If it floats, what's got to be true? What's equal?
Buoyancy and gravitas.
The buoyancy force up and gravity down. It's just a regular old force problem, right? So you got buoyancy
It's in water, right?
and you've got mg. And we're talking about it being in water, okay? So let's see. If it's going to float, the sum of the forces must equal 0. Buoyancy must equal mg. So rho Vg for the fluid must equal mg for the object. Okay, mg for the object is pretty big. 130 times 9.8. Okay, over here, what goes in here? Okay, 1,000 for the fluid, assuming water. V is what we're solving for, right? Ooh, can we solve for something other than V? We're looking for the height that it sinks in, right? How do we get that?
Divide by area.
Ooh, we can do that, right? Because the volume of this thing is going to equal the area of the base times the height, right? So the area of the base times the height. What's the area of the base?
0.01. 0.0.
0.01,
No, 0.0.
right? Meters squared times the height, and then I got a 9.8 in there, right? So the 9.8 cancels out of both sides.
Yeah, 0.1.
Wow, what height would I need? 13 meters?
Yes.
So does it float?
Yes.
It does. Surprisingly enough, it does float. But it sinks down in 13 meters before it can float.
It's already touching the bottom. So
Yeah, by then it might be touching the bottom.
Great number.
So if
Okay?
13 meters.
So
is
person,
quite
say
what
a
it is.
person is of a specific density or whatever, and so only to this point will we be able to, like, right here, right at this point will we be able to float, so he's on the ground, right? I mean, right?
Yeah, he could turn his
Well, assuming he can't.
snorkel.
Actually, here, let's go back and take a look at this a little bit differently. Well, actually, you know what? We'll do it in just a minute. Okay? I want to talk about what happens if something sinks. Okay? All right, so if you have an object that sinks, so if it floats, these two will be equal. If it sinks, they won't be equal. So you have a couple of different options for what they might ask you. All right, so I have an object. This object will sink. Okay, it's going to sink. So what they do is they suspend it by a spring scale. And they ask, what's the spring scale going to read? Okay?
Okay.
Okay, if you're holding it up in the liquid, and they want to know what the spring scale, the force meter, reads, what kind of problem is it? Is it kinematics? Is it energy? Is it momentum? Is it forces? Forces. Okay, what do we always do with force problems?
Free body down.
Free body diagram. What's my free body diagram look like?
Well, we have gravity going down,
Got an mg, what else?
buoyancy going up,
Buoyancy going up,
and we have a spring going up.
and we got the spring scale going up, which I'm just going to call tension if that's okay.
Yeah, that's
All right? So the spring scale is going to read the tension. Okay, if it's staying right there, then those three must equal out, right, to
Assuming it's
zero.
stable, right? It's still.
Yeah, sum of the forces equals ma, but assuming it's not accelerating. That means buoyancy force plus tension must equal mg. So if you want to find tension then, tension is going to equal mg minus rho vg, right? M is the mass of the object. Rho is the density of the liquid. Is V the volume of the object this time?
Volume of
Yeah.
the fluid.
Yeah, V is the volume of the object, whereas over here, V was only this volume, right?
You gotta do rows.
Yeah.
Okay?
Wait, isn't V just the volume displaced, which is equal to the
In this case, this would be the volume displaced. It's always the volume displaced,
just equal to the
but in this case, it's the volume of the object, right? When the object is floating is where you have to really be careful, or when it's only partially submerged. Okay? So will the tension here be greater than or less than or equal to mg?
Less than.
Less than. It's gonna. Sometimes they call this apparent weight. That's what you experience when you lift somebody in the swimming pool. You're only lifting up with what they apparently weigh, right? Because the buoyancy force is canceling out part of mg. So you only have to lift up with a small force to lift it. All right? Okay. What if they cut the string? Then what happens?
Wait, you cut the string?
Yeah. What if you cut the string? Then what happens?
It'll sink.
It'll sink. And in fact, whoa, then what happens is this. F equals ma. If you cut that, then it will accelerate down, right?
But what's the acceleration?
Well, you can calculate it, can't you? At least initially, assuming at the beginning there's not too much drag on it. Now in a liquid, you get drag pretty quick as soon as it starts moving, right?
And plus it's a square.
Yeah, plus it's a square. But you could at least find the initial acceleration, right?
More.
At the beginning. All right? Okay. So what if we have something that is gonna float, but we submerge it?
Let's make it a spherical cow.
It's a spherical cow. It was going to be a beach ball, but I like the spherical cow. All right, and you suspend the beach ball from the bottom by a string. Now what do the forces look like?
And
Oh, that's not.
You got a little bitty mg,
Big ones.
you got a pretty big tension, and then you got a buoyancy force, right?
I'm going to just almost.
And if it's stationary, then those three should be equal, right? Buoyancy force up should equal these two,
Okay.
right? What if you cut the string?
It would-
Then it'll accelerate up, just like
Shoot up.
any other object. Yeah, you've all done this.
Yeah, like you get on top of it.
Yeah, you've all taken a beach ball and submerged it, and then you walk up to your friend, and then when they're not suspecting it, you let go and it shoots up at them, right? You've done that. Couple of quick things about this, everybody. Couple of quick things, real quick. Shh, look at me, look at me.
I see you.
All right. First of all, Archimedes, way back, crazy guy Archimedes, apparently was taking a bath when he discovered the idea of buoyancy force.
Oh, yeah, and then he ran out of his bathroom.
Yeah, apparently he jumped out of his bathtub. He was so excited, ran down the city streets yelling "Eureka" while he was
That's 'cause
naked,
of that
right?
crown of gold, right?
But it didn't mean much because in Greece you were allowed to be
Yeah.
naked anyway.
That was crazy Greece.
Kids did get close till they were like 10.
Get him to the beach.
Hey, it's cheaper that way. I should have done that. All right.
There's laws against that.
Whatever. All right, rho times V. What's that?
Density volume?
What's
It's
rho
mass.
times V?
Mass
Ooh, everybody pay attention. Mass of what?
of the fluid displaced.
Mass of the
Fluid displaced.
fluid. Mass of the fluid that's displaced. So Archimedes figured out that the buoyancy force is actually equal to the mass of the fluid that's been moved out of the way. Kind of crazy. Actually, not the mass, of the weight, the force, gravitational force of the fluid moved out of the way. So this is the weight of displaced fluid. Okay, so here's the deal. Somebody asked about specific gravity earlier. Specific gravity is the density of whatever the object is divided by the density of water. If you have a specific gravity of greater than 1, then it'll naturally sink. And if you have a specific gravity of less than 1, then you'll naturally float. Okay, steel. What's that?
What if it is one though?
If it's 1, then it will be neutrally buoyant and it will float. Completely submerged. Like a fish. Or a sub. Alright, now listen. Okay, ships are made of steel. Steel has a density greater than water. So therefore, steel should sink. But steel ships float.
They're hollow.
Okay, here's why. If you want to float, you have to displace a weight of fluid greater than your own weight. And how do you do that? You make a ship into a boat shape.
Eureka!
Eureka!
Never been on the streets naked.
No thanks. I don't think anybody wants to see me do that, Rudy.
Um,
I'm no.
okay, now look.
I can't run naked.
A boat floats
Oh my God.
because it's displacing this volume of water. Right? It has taken the ship and made its effective density less than that of water. because you're incorporating the density of all the air pocket inside the ship along with the density of the steel.
And the people.
And the people, so it weighs less. By the way, if you fill this ship with balloons, like regular balloons, you blow them up, put them in, or ping pong balls, it will sink farther in. Because you're adding weight to the object, right?
Oh, yeah.
Densely.
So if you fill it with people?
Now, if you fill it with helium balloons,
Or helium fuel.
It would flap
then it will go,
away.
Yeah, because instead of air there, it's helium.
right.
Mr. Rudy, we should do a problem with how many balloons it would take to lift the house one up.
We worked this one time. I had everybody figure out what their volume needed to be for them to float. We should do that, yeah.
I want to float
Where
away.
did the hold up?
Wait, float, assuming.
All right, now, everybody, if this thing springs a leak, okay, we all know that a ship will sink if it springs a leak, but mathematically or physics, why to that is because, look, once this thing fills up with water, it's only displacing this volume,
Which is all density.
which is not enough buoyancy force to hold the ship up. Does that make sense? Yeah, because it's made of steel.
It was so much crap.
So, like for instance, the Titanic was supposed to be unsinkable because it had watertight chambers. So what would happen is that if the ship, okay, if the ship happened to hit something and this chamber would fill with liquid, no problem. You'd still have all these other air pockets inside, right? The problem with the ship is these air pockets didn't have a top to them. And so the ship tilted. And when it tilted, the water level was like this as it tipped over. And so it poured in from one to the next. And they all filled in. So it went down one by one container.
Why didn't they
And
have a
that was an intense movie.
Who would have thought?
Intense.
Actually, what happened is they had several of the, I think it's because of the way they sliced and hit the iceberg, they sliced through a couple of the containers.
Went through
Yeah.
4 of the 9.
Yeah, instead of just a couple. I think they said if any 2 or 3. And they had one more than what was allowable filled up because they turned. If they'd have just hit the iceberg straight on,
But then.
piece of cake. The ship would have been crippled, but it would have only damaged one container.
But then if they would have been going at the,
Well, no, they just didn't turn
speed
quicker.
that
Yeah.
they're supposed to be
If they would have
going.
been going at the speed they were supposed to in fog,
Yeah.
then they wouldn't hit it anyway,
They
probably.
should have done what my mama did and hit the brakes.
You can do that on the Titanic, hit the brakes.
All right,
Drop all these anchors in the board.
so there you go, everybody. Shh, that's buoyancy force. Questions on buoyancy force? Everybody, listen. If they ask a question about buoyancy force, you revert everything back to F equals ma.
Right about that Titanic.
Okay, because it's just a force problem, right? It's just another force. Okay, now we need to continue into our dynamic fluids. So here we go. On the bottom of page 11. Bottom of page 11. Fluid dynamics. Okay, these are the very basics of moving fluids. Okay, we're going to identify what we call an ideal fluid for our basic beginning of study fluids. Fluid dynamics, anyway. All right, first of all, we're going to identify what we call an ideal fluid. Number 1 is the fluid's going to be incompressible. Therefore, the density in the fluid remains constant at all times. Now, in a liquid, that's a pretty good guess. In a gas, if the gas is moving very fast, that's not a very good guess. So we're talking about low-speed dynamics. All right? We're going to talk about the flow not rotating. So we don't have any rotational dynamics. Thank you. No rotational spinning vortices. The flow is steady, it doesn't fluctuate versus time, and it's non-viscous. That means there's no friction. We're assuming that our fluid is frictionless. Again, it's got to be low speed.
So no dragging for you.
No drag in our fluid. Now, in a gas, if you're moving slow, great. In a liquid, even moving slow, all right? But those are going to be our first case estimations or approximations so we can understand what fluid flow is like.
Okay, so when you mean low speed, it's just moving slowly.
Yeah, and the key thing is that we end up with what's called laminar flow. Laminar flow is a flow in which the fluid, a particle in the fluid will never cross the path of another particle. Okay? Now, you've seen those commercials, right? Where you got a car and the car is in a wind tunnel
Oh, yeah.
and they have smoke going past the car. You've seen that, everybody?
That's just
Yes.
scary.
Okay? And the smoke comes by and goes like this.
Oh.
Oh, yeah.
Okay. Okay, those are called streamlines. Now, if this is truly this ideal fluid in laminar flow, what ends up happening is the smoke particle here and here and here, they will never cross each other's paths. Now, their paths may get closer or farther apart, but they'll never cross each other's paths. If they cross each other's paths, that's called turbulent fluid, and turbulent fluid is a lot more complicated. All right? So, if it comes back over here and starts doing that, then what we're studying won't work that great. Okay? Now, here's the really cool thing about this. If we have laminar flow, then these particles, because they never cross each other's paths, it's like we have a tube here that comes out over here. It's like a pipe of fluid that starts here and ends up over here. Okay? Now, if we have a pipe of fluid where none of the particles inside ever go out, then that means the mass flow rate in, the delta mass over time going in, must equal the delta mass over time coming out. Does that make sense?
Yes.
Yeah.
It's got to go out. It can't stay in, and you can't get more out than you put in, right?
Or less.
Now, because the mass, or because the fluid is, density's not changing, you can also change this to the volume flow rate going in equals the volume flow rate coming out. Okay? Now watch this, because this is pretty slick little trick. There's the area, and the particle moves from here to here. Okay? That's a delta x in a delta time. Ooh, that's area times
The height, I guess. Just like
Velocity.
velocity. Thank you. So area times velocity going in must equal the area times the velocity coming out. All right? That's called continuity. Continuity, it's called the continuity equation. Continuity is the statement of conservation of mass, is what it is. Okay? So the volume flow rate in must equal the volume flow rate out. So everybody, you might want to write this down just in case. This is volume flow rate. Okay? Now watch this. You see the area coming out over here?
greater,
See the area going in over here? They're not the same.
so velocity decreases.
So where's the velocity greater?
At that A1, up there.
In the drawing I have, the velocity going in must be greater than the velocity coming out. Because the area has increased on the outbound side. Okay?
Yes.
Now, let me explain to you how a plane works. Okay, a plane has a wing, and the wing has a shape called an airfoil. The cross-section of a wing looks a lot like this. Okay, when air comes up like this, it has to decide whether to go over or under. Okay? So one particle will go over and one particle will go under. This particle up here is going to go straight by. It's far enough away that it doesn't matter. And down here, it's going to go straight by. Okay, now look what happens. You see this area here? And you see this area here? There's a difference in area. Where's the air going to go faster? Here or here?
Slow.
There.
There.
Because area times volume 1, smaller area, velocity,
Velocitile.
times velocity 2. So this velocity is greater than this velocity. But look at the bottom side of the wing. See this area here? See this area here? And it's roughly the same, right? So the velocity here is the same as this velocity. So this is V1 here, and this is, V1 here. This is V1 here. So wait a minute, the velocity is greater here, and it's slower here, right? Okay, that's the key. That's step number 1 to the why a plane flies. All right? Let me give you step number 2. Yes, ma'am?
How does they fly upside down then?
I'll explain that in a minute. That's an excellent question. How can a plane fly upside down? Because wouldn't the wing then try to drive the plane into the ground?
You would go really, really
The
fast.
answer is yes. And on like Formula One cars, they will have a wing on the back of their car, but the wing is upside down because you don't want your car to leave the ground, right? So as they go faster, the wing pushes the car onto the ground. You already know this. This is called continuity equation. Let me write it over here. I forgot to put buoyancy force over here. All right, everybody already knows continuity equation because you all know how to squirt somebody with a hose.
I close off the
Oh yeah,
part
you
of
just
it.
kind of.
Yeah, you take the end of the hose and you stick your thumb over it and you cover up part of the nozzle or end of the hose where the fluid comes out.
And it speeds up.
And so it must speed up because you've decreased the area for which it comes out and it flies out really fast, right? And it goes farther. You also already know how to blow out a candle. How do you blow out a candle?
I've never been able to do that.
With your
That's
fingers.
right. You do this.
You do this.
Actually, I forgot to bring my candle today. Usually I'll have a candle up front and I'll ask somebody, usually the loudest person in the class.
Yeah.
Hi, Dan. And I'll ask them to come up and blow the candle out by doing this. And they can't do it.
I
Oh,
can.
really?
And they, how do you blow out a candle?
That's just
Now,
your
bad
will
breath will
explode.
not blow the candle.
Just watch.
Garlic.
We should do that next class period.
Breathe garlic on.
Okay, why does this help you blow out a candle?
Because decreased areas available.
Yeah, because you've decreased the exit area, therefore the velocity of the air must go higher, right?
Whatever.
Excellent. All right, now.
You can always place a cup over it and have it burn out the rest of the
Yeah,
box.
you
Oh,
go.
you didn't hit yourself.
That'll work.
But there's a hole in the cup, so it doesn't work.
Well, if it's short enough, then it can completely cover it.
Hey, by the way, any of you ever gone canoeing or whitewater rafting? Anything like that?
Yeah.
Okay. If you've gone, where does the water flow the fastest?
Where it's
And
skinny,
the rapids, there's not much room.
Yeah, it flows fastest wherever the river is narrower or
Shallow.
shallow.
shallower, because it's less flow volume, right? Flow area. And also where there's rapids, where there's rocks.
Yeah, the rocks are.
The rocks take up area for the water to go through. Therefore, the water must shoot by the rocks faster because there's less area for them to shoot through.
Oh, where there's a waterfall.
By the way, if any of you have ever gone downtown on a windy day
Yeah.
and you're in the streets there and the wind is just like whipping between the buildings,
Yeah.
and why is that? Because there's less area for the air to get by. And so therefore it has to shoot by between the buildings really fast. Okay? Yeah.
Like in Chicago, they were building that building, and it was really narrow and it was really tall. And they started building it, and like they only had it like up so far. But the problem was they had to stop building it because the wind. Now it's really windy in Chicago. The wind started picking up so fast, in between those two large buildings, that the car started raising up like this much.
The cars started
The car
lifting.
started raising,
I didn't hear that, but
It's up. Well, I read it in the magazine about buildings.
It's true. That's what they said when I went
I heard that.
really? Wow.
It's not all of these architects.
All right. Now, dynamic fluids. Dynamic fluids, right here. We've done number 1. Here's our second one you need to know. The second one we need to know is called Bernoulli's equation. Okay. What's that? Y is the height. I'll show you this. Okay, everybody, they call it Bernoulli's equation. It's kind of a sordid story, but the father Bernoulli, I don't remember if it's David or Daniel, I don't remember which one. I think I don't know. Anyway, the father always wanted to invent something or discover something important, and he never quite, I mean, he was a good mathematician and scientist, but never really came across anything, you know, spectacular. And so he was kind of frustrated. His son was very bright, and his son came up with, we believe his son came up with Bernoulli's equation. Okay?
No, actually, he killed his father after his father actually came up with the equation in order to claim credit for it.
No. So what happened is his son showed the equation to his father, and his father goes, I don't think that's right. You better go back and work on that some more. And so then his father published the equation.
Oh, wow.
Yes. So they just call it Bernoulli's equation. They don't give it the first, you know, they don't attribute it to either one because they're not really sure who came up with it. They think really the son did. Anyway, yeah, kind of a sordid story. All right, Bernoulli's equation is conservation of energy applied to a moving fluid. Okay? Okay, and it looks like this. P plus rho Gy plus 1/2 rho V squared at one spot must be equal to P plus rho Gy plus 1/2 rho V squared at another spot. Now, there's a lot of P's and rho's and G's and Y's, and they all kind of look the same. So make sure that you know which one's which. All right? I want to exaggerate them a little bit. All right, now this looks really, really complicated. Actually, on your equation sheet, they'll write this equals constant. Okay?
Oh, that's net change.
So there's no change in this total value anywhere along a streamline. Okay? So, what the heck? How do we apply this? Okay, number one, let's apply it right here. Here, I'll just do it down here, the way they normally do it. Okay, if I've got a tube that looks like this, okay? And I'm looking at the pressure here, and the pressure here as the fluid flows through, okay? From point 1 to point 2. Okay? Now, P plus rho Gy plus 1/2 rho V squared. Okay, rho Gy. Rho is the density of the fluid. G, of course, is 9.8. What the heck would Y be? Y is the vertical location. Okay, as this goes through from here to here, notice that the vertical location here and here are the same, right? So won't rho Gy here and rho Gy here be the same? Are we okay with that? So for our case,
So
this
relative
one
to the ground.
and this one are the same, so they cancel out.
Okay, but relative to the bottom of it.
Yeah, but overall, the average height here and the average height here are the same, right? Okay?
Just for my sense.
All right, now,
So as long as it's like in the middle, what if it's like the top?
well,
very
what
top?
if it was like this? And you went from like this up to like that. Then what you would do is you would call this y equals 0, and then that would be whatever that y is.
Well, they'd just be from the bottom of the tube, right, at that point, not that huge distance.
Generally what they'll do is they'll tell you that the top of the tube is located so much higher than the bottom part of the tube. And then you'll have your height, or your y. Or you would do the middle of the tube.
Well, I'm just saying, yeah, you get the middle or whatever, and then you get the middle of the one at the top, right? And then the distance at the top is just from the middle to the bottom of the top.
That was confusing.
From the middle to middle. Make it easy.
Okay,
That
so
is y.
middle to middle, that's the
Yes,
whole thing?
that's the easiest way to do it.
So is it kind of like
Because that gives you your
delta Y?
average.
So couldn't y kind of be like a delta y change in display?
Yes.
So since in this case.
Hey, some of you are starting to notice that this looks a whole lot like things we've seen before. First of all, P plus rho Gy looks a whole lot like P plus rho GH. And also, some of you are noticing that rho gy looks a whole lot like mgh, and this looks a whole lot like 1/2 mv squared.
Yeah, it's directly.
So you apply this just like you do energy. Remember, in energy, all you do is look at one spot, another spot, and say, what kind do I have here? What kind do I have here?
Oh, that stuff. I love that.
All right. So right here, we do the same thing. What's the P plus rho gy plus 1/2 rho v squared here compared to here? Piece of cake. It's really not that hard. It looks ugly, but it's a piece of cake. All right, everybody. How is the velocity here compared to here?
It's much lower.
Lower. At 1 is lower.
Okay, so we have a small velocity here, but we have a large velocity here. Okay, now look. How is it possible for this equation, which now looks like this, because these two have subtracted out, how is it possible for this equation, to this side to equal that side, when I have a huge V here?
The pressure is
The pressure must be different. Where is the pressure greater?
where the velocity is lower.
The pressure is greater where the velocity is lower. Okay, Bernoulli teaches us one thing right off the bat. Whenever the velocity of the fluid is greater, the pressure inside the fluid will decrease. And whenever the fluid is slower moving, the pressure inside the fluid will be greater. So they're inversely related. So as velocity goes up, pressure in the fluid goes down. As velocity goes down, pressure goes up. Now look, let's look at our wing again. What kind of velocity do I have above the wing? Big. What kind of velocity do I have below the wing? Small. So how is the pressure on the bottom compared to the pressure on the top? You've got a great big or bigger pressure on the bottom, and you have a smaller pressure on the top. The difference in pressure gives us what we call lift.
Okay, wait.
Okay? That's lift due to the curvature of the wing. Okay? Now the question was, is how does a plane fly upside down? Because then what would happen if you flew your plane like this? Then it would get lift downward. All right, the way they do it, the easiest way to do it is to do this. Okay? Now look, you're going to get lift down, but the air is going to hit and bounce off this way, and you're going to get an impulse up. And that impulse up is greater than the Bernoulli lift down. So when you have it like this, you can get lift from the Bernoulli curve, and then you also get lift from what they call angle of attack, because the air hits and bounces off. It's a momentum collision. All right? Okay, so there you go. As velocity increases, pressure in the fluid decreases. Okay? All right. Here, I'll demonstrate that for you real quick. Piece of paper, need a piece of paper. Oh, yes. That's correct. That's correct. I was going, man, I don't remember that, but that's in the RE homework. That's right.
Try to cut it in half.
Vertical is shit in the
There we go. Strip. All right, so look.
Are you gonna blow it?
Now I'm going to just blow this way. Why? Does it go up? Because the what? Because the what and the what and the what?
Oh, I remember that.
Has a lower pressure.
Hey! Marcos. No, go. What? Marco. Come on.
Why do you always do that?
All right, when I blow through the air here is moving faster, so what happens to its pressure? It goes down. But the air down here is not moving, right? So the pressure down here is greater than the pressure up here, so this gets pushed upwards. Right?
Blow below it.
Blow below it? Now I'm hitting it and making it go up. If I blow, like, what, down?
They don't do anything.
Yeah.
Okay, now.
No.
So since I'm blowing here, this is
What the heck?
Actually, that's the classic trick. If you take two empty Coke cans, sit them next to each other, and you blow in between, you can make them hit. You ever done that?
Yeah.
Wait, what?
Okay.
Do it again.
Bottle of water. I can do
It's a famous bar trick. You have two empty Coke cans, you blow in between. When you blow in between, the lower air pressure here and the higher air pressure on the outside, the higher air pressure pushes them together and they hit.
Look what I have.
2 calculators, would that work?
A kazoo. All right, listen. We are just about out of time. On page 13, example number 2. You need to know this problem. It's on the homework, and it's a high likelihood of you seeing it again sometime.
Where did I
Maybe
on a
Thursday.
Let me see. Yeah, let me see.
Make sure you understand it. Page 13, example number 2.
13.
Oh, lucky number 13.
It explains, hey, listen. It explains how you can figure out when you punch a hole in the bottom of a container of fluid, how you figure out the velocity of the fluid coming out.
Like on the cooler thing?
All right, if you have a container like this and you punch a hole in the side, okay, the fluid's going to shoot out, and they're going to want to know the velocity of it. You apply Bernoulli up top and Bernoulli down below, actually right here. Okay. And then, yeah, guess what? It's going to be a trajectory motion problem.
So wait, but I mean it's a constant flow. So I mean, how we define the mass of a constant flow?
All right, let me just do it quick. Okay, this is open to the atmosphere, this is open to the atmosphere. They're both open to the atmosphere. Therefore, the pressure here should be atmosphere and atmosphere.
So you can take those.
So they cancel. All right? Notice down here, y equals 0. So that goes away.
But there it is.
Right here, that's a distance I'll call h. Okay? Up top, how fast is the water moving as it exits here? And not very, right? Really slow
Yeah.
compared to here, right? So that's going to be 0 essentially, right? So I end up with, at the top, rho GH equals at the bottom 1/2 rho v squared. Does that look familiar? MGH equals 1/2 mv squared.
That's not right.
G cancels and I end up with 2GH square root, which is the exact same thing you get if you use conservation of energy. Isn't that cool though?